Our next speaker is Rocío Mercado. She's part of the molecular AI group at AstraZeneca. Her work focuses on using deep learning methods for graph-based molecular design. She will talk about molecular design using graph neural networks. Welcome.
Thank you so much. Sorry, I just need the clicker. Okay, thank you so much. Thanks so much for the introduction, and thank you so much to the organizers for, first of all, holding this event, and then also for giving me the opportunity to speak here. So I'm very excited today to tell you about some of the work that we've been doing in our group at AstraZeneca, and how we use deep learning for molecular design. So today I'm specifically going to be telling you about one of our recently published platforms for this, so it's called GraphInvent. So I'm going to get right into it and start by talking about how AI can actually help the drug development process. So I'm going to illustrate this with a bit of an oversimplified example first, but hopefully it gets my point across. So let's say that you know that a certain protein plays a crucial role in a given disease. And maybe perhaps to attempt to find a cure to this disease, you can try to inhibit the function of this protein, excuse me. One of the ways in which you could do this is, let's say, you try to identify a molecule that can bind in this very well-defined binding pocket. So it's not as simple as it sounds. However, as there's a bunch of different criteria that you have to actually optimize in order to find the best molecule. So first, the first criteria is actually finding a molecule that binds to a known target. So this would eliminate a lot of molecules right off the bat. Then you'd want to make sure that you the molecule that you're taking forward, that it's very selective for the protein that you're targeting. So you don't want it to bind to any other protein, just the one that you're interested in. So maybe you make some small modification to your candidate molecule. Then you also want your molecule to be novel. So here you would make maybe further modification in case the previous molecule you had has been previously patented. You want to definitely be moving forward with a new molecule. And then you can make further modifications related to the optimizing the physicochemical properties of the molecules that you're studying, and so on. You can continue to do this for the rest of the properties on your list. But this is a very difficult problem, not only because you have a very large number of interdependent properties that you're trying to optimize over, but also because you have a very large space of potential solutions. So the space of theoretically possible drug-like molecules is estimated to be between 10 to the 20 to 10 to the 60 number of molecules, which is quite enormous. So this makes it a very difficult problem to solve. And traditionally, the drug discovery process involves screening large libraries of compounds. You have scientists who are proposing changes to these promising molecules. You have teams communicating back and forth over many cycles, many iterations. And in the end, you realize that maybe you spend a few years in this initial drug discovery phase. But one of the things we're interested in is seeing if we could actually use deep learning to accelerate this drug discovery process. And here I mean that not only do we want to shorten the time that we spend in this initial drug discovery phase, but we would also like to be able to find better solutions, so increase the likelihood of success in any of the candidates that we take forward to the preclinical and in the clinical trials. So now I'm going to talk about the field I work in, which is deep molecular generative models. And deep molecular generative models are tools that we can use to speed up the drug discovery process by generating molecules only in these promising areas of chemical space. So here we have a pink box that represents our deep generative model in the center. And what this model does is it would take as input all the desired properties that we want our molecules to have. So here again is the physicochemical properties, the novelty, the desired target. And what the model will do is it will do some optimization in a latent space, and it will output to us only the molecules that have those desired properties. So this is a big area of research, and there's been a lot of different deep molecular generative models that have been developed in the past few years. A lot of them have come from our group, and they can largely be classified into two classes. So we have string-based approaches, graph-based approaches. I've also put a bit in gray the 3D approaches, since this is a more emerging, very hot field, but I won't talk about it here. So in string-based approaches, we can actually use the string representation for molecules in order to study them. So there's many methods from cheminformatics. There's many ways that we can actually represent molecules as strings. And this opens us up to all of the methods from natural language processing in order to study molecules. Similarly, we can also use the molecular graph representation, which is a bit more natural. And both of these methods have their own advantages. I myself work in graph-based methods. But within each of these two classes of molecular generative models, we also have different schemes that we can use for generation. So the first one is we can generate molecules in a single-shot way. So let's say here, every time we sample our model, we sample an entire graph all in one go. So this would be a single shot. We could also sample new molecules in an iterative way, where every time we sample the model, we're instead sampling a single node at a time, and in this way building up our entire molecule. So we treat it more as a sequence. And in general, iterative methods perform a little bit better, although there is advantages to each as well here. Okay, so now I'm going to tell you a little bit about GraphInvent, which is the platform that we've recently published in our group. So what is GraphInvent? It's a deep molecular generative model that is graph-based, and it uses an iterative approach to molecular generation. So the GraphInvent structure, the models in GraphInvent actually consist of a tiered deep neural network architecture. So the first block is a graph neural network. Second block is a tiered feed-forward network architecture. And so I've put the link there to the GitHub repo, as well as to the publication. I'll put it again at the end of the talk. But the code was written in using PyTorch, and you can run it on a CUDA-enabled GPU. But how does it actually generate new molecules? So if we focus on the figure on the left here, then we start from a given input graph. So here the graph has 3 nodes. We input it into our model. And what the model outputs to us is a vector that contains the probabilities for all the possible ways in which we could grow our input graph. So if we sample from this long vector, we sample an action, then we can apply that action to our molecule. So here we grow the molecule by 1 more node, and then we feed that molecule back into our trained model. And we repeat this process, feeding the molecule back into the model until the model says to stop. So we've, this is enough steps. And in general, GraphInvent generates structures probabilistically, 1 atom bond at a time. It can actually start generating new graphs either from empty or non-empty graphs. And the structures that are generated by models in GraphInvent tend to have a very high validity and diversity. So GraphInvent uses the matrix graph representations, as I've shown you before. So what this means is the input is an undirected molecular graph G, which is a tuple of nodes and edges. And what this practically means is that we can represent all of the molecules in our training set using these 2 different tensors. So we have a node features matrix X, which encodes the identity of all of the nodes in our molecules, and we have the adjacency tensor E, which encodes not only the way that the nodes are connected, but also the identity of all the edges that are linking the nodes. So how does it work? Again, we take our node and edge features the adjacency tensor, and we feed it as input to our generative model. And what the model outputs to us is the same tensors, but they are all augmented further by either 1 edge or 1 node, depending on the action that was sampled. Then we take our output, and we feed it back into the model. So now our output is our input. What the model does is it gives us back the graphs further augmented by 1 node or 1 edge. And we repeat this process until the model is finished. So the first block of the models is a message passing neural network, or an MPNN. So here the input to the MPNN is the node features matrix and the adjacency tensor. What the MPNN outputs to us is these two items. So one is the node embeddings matrix, which is a matrix of stacked node embeddings for every single node in our input graph. And then we have a vector, which is our graph embedding. And this is a representation for our entire molecular graph. And there's some very nice properties that these embeddings have. So we can take these learned node and graph representations from the MPNN layer and feed this into the second block of our model. So this is the global readout phase. And what the global readout outputs is an APD. And what this is an action probability distribution that tells us how are we going to grow the molecules that were in the input. And it's split into three terms. So fadd, fcon, and fterm, more or less, they have these shapes. And what these are, fadd is the encoding the probability of adding a new node to an existing node in the graph. Fcon is encoding the probability of connecting the last dependent node to another node in the graph. And fterm is giving us the probability of terminating the graph generation. So all of these make up one probability distribution. So they're all softmax, and they should all sum up to 1. And how do we actually teach the model how to generate the correct action? So the goal of the model is to minimize the KL divergence, where here the KL divergence between the target APD and the predicted APD. And the target APD encodes the correct action. The predicted APD is what the model is predicting that we should do to this input molecule. And the best model in Graph Event actually uses the GNN architecture, which is the gated graph neural network architecture. I won't go into the details here, but this is what the message passing phase of the GNN looks like. This is what the readout phase looks like. And this works extremely well for our models. Then the GNN is followed by the global readout phase that I've shown here, or this is rather the best one that we found in our model. So it's a series of feed-forward networks that take as input the learned node and graph embeddings. And we compute the three terms of the APD separately, so fadd, fcon, and fterm. Once we compute each of those terms separately, we concatenate them, softmax them, and that's our probability distribution. So our models, we have benchmarked them using open source benchmarks, and we find that our models perform on par with state-of-the-art models. For details, I encourage you to see our publication. I've linked the GitHub repo, which contains links to the publication, as well as the repo to the benchmark that we use. It's called Moses. And in general, the structures that are generated by our models have a very high diversity and novelty. We also find that the models can learn from very few data points. There's a relatively low % validity in our models, so only 95%, which is not so low when you also consider the fact that we don't encode any expert knowledge into the models. There is no chemical rules information. The models learn the chemistry just from the training set, but this still gives us something to try to improve. We would also like to improve on the computational cost that is currently associated with the graph event models. So they're generally a little bit more expensive than string-based methods, for example. Okay, so summary. So here's what I covered today. So AI can be used to accelerate molecular design and the drug development process. And I've shown you how there's two main classes of generative models. So we have string and graph-based. We also have single-shot and iterative approaches within each class. And Graph Event specifically is a platform that uses graph neural networks for graph-based iterative molecular generation. And it performs on par with state-of-the-art molecular generative models. So hopefully you take away that graphs are very powerful molecular representations for these tasks. So now I'd like to thank you all, the audience, for your attention. I'd also like to thank the Gaia organizers, as well as all my colleagues who worked with me on this project, as well as the molecular AI team, who's fantastic. I've put up a link to the repo, which contains links to not only the code, but also tutorials on how to use the code, and links to the publications. And finally, I just want to advertise that we have master's and PhD thesis opportunities for autumn next year. So if you're interested in that, please contact Ulla Enquist. So thank you.
Thank you. Very interesting to see this technique used actually in real world. In graph neural networks is sort of like a theoretical or academic research field in general, but it's really cool to see that you're able to use it. So we have a couple of questions from the audience. First of all, we have Elin, who's asking, how much time does this approach shave from the classical time frame of developing molecules?
Well, that hasn't been measured yet because it's also not going to, you can't really switch completely to doing it all using these approaches, right? You'd have to start to slowly integrate it into your pipeline. So you might start to see some improvements slowly, but I can't answer that question. Maybe in a few years we'll see a publication from someone who has studied this, but I don't have an answer now.
Okay. We also have a question from Jesper, who's asking, have you thought about different representations that you use for in the graph, like other latent spaces like Poincaré space or something like that?
We have used other molecular graph representations. So I played around with those, which features I wanted to include for describing the nodes, which edges and so on. But in the end, I chose the smallest representation possible so as to make the models train as quickly as possible. Because the bigger you make, the more features you choose to include, the bigger all your matrices are going to be, and then more expensive is your models. So.
Right. So that was actually a question that I had. Like, how big molecules are you able to generate here?
I've gone up to, what is actually the largest? In the 50s of 50 number of nodes, where the nodes are all heavy atoms. So we're not including the hydrogen atoms. But there is other graph-based methods which have gone on to bigger molecular graphs, including thousands of nodes, but they used a different approach than what we have. So we're hoping also to be able to scale up.
Okay, cool. So I also noted that this gated graph neural network paper is quite old, and people have been experimenting with a lot of different activation functions and so on. Have you tried changing that approach?
Yes, we actually compared the GGNN to a few other MPNNs. We did still find the GGNN was the best, and we're currently exploring different graph-based architectures as well in our models. So we'll see if there's any better performance.
Okay. Cool, interesting. So it's also the fact that, I mean, you're predicting the next action, and that seems to be like a probability. So why don't you use like log loss or cross entropy loss, and why do you use this KL divergence?
I wish I had a good answer for that. I found it to work the best, actually. I tried a few different loss functions, and this is what I saw was working the best in the model, so then I went with it. And I've seen a few other papers that use it, but I could explore different options if I see a good argument why I should be using one particular thing and not this. But it works.
Okay, do you have any intuition to why that's the case?
No.
Okay.
Sorry.
Okay. So another question from Jesper. Is there some approximate method of estimating the quality of some novel APD? I'm not sure I understand the question. Perhaps you do.
Novel. No, I don't understand actually, because we wanted to match that which is we know is to be the ground truth, and we generate the ground truth in the pre-processing phase. So we pre-process all the training data and we generate all the ground truth APDs. So we wanted to match that, but I don't know exactly what's the question.
Hopefully Jesper is happy with that one.
Yeah. Okay.
Okay. Thank you, and welcome Anna with the flowers.
Oh, thank you. All right, thanks so much.
Okay, thank you.